Okay, integration by parts is one of our advanced integration techniques. It's really good for the product of two functions, and it's one of the first techniques we should rely on when our basic integration rules fail. Okay, so we're gonna we see that the integration by parts definition is based off of basically the product rule. So I'm going to start with the derivative. I started with u times v, and I'm going to take the derivative of u times v, which gives us um, left d right, so u dv over dx plus v times the derivative of u du over dx. And I'm just going to simplify that to say that the derivative dv dx is equal to dv, and du dx is equal to du. Okay, so this seems like this next step seems a little silly, but what we're going to do is take the antiderivative of both sides. So on the left, the antiderivative of the derivative of u times v is u times v. And then the right, I'm just going to leave it times the integral of du. Okay, so what I'm going to do next is move over the integral of v du. So I get uv minus the integral of v du is equal to the integral of u dv. So I end up with, I'm just going to rearrange this, or the integral of u dv is equal to u times v minus v times du. This right here is the formula for integration by parts. So we see that if u and v are functions of x and have continuous derivatives, then we end up with the formula, the integral of u dv equals u times v minus the integral of v du. Integration by parts, I always remember the right side of the equation as ultraviolet voodoo. So that's how I remember which pieces go where. So the weird thing about this formula is that it expresses the original integral in terms of another integral. In other words, there's another integral inside of our expression, but it's something that we hope to be able to integrate to like an integral that is easier to integrate than the original, so that we can go ahead and evaluate that the voodoo part of the integral. Okay, so let's do an example. Oh, one more thing. So in general, what we're going to do is we're going to pick out part of the expression to represent u and part of it to represent dv. Dv is, you have to be able to integrate it first off. And I usually pick the u to be the easier part of the equation. So if I use the integral of x e to the x dx, I am going to try and make the u equal to x because that's pretty easy to take the derivative of. Okay, now I will make the rest of this dv equal to e to the x dx, and my goal is to take the integral of that so that I end up with my v value. So the integral of e to the x dx is e to the x. The integral of, or the derivative of u is du equals dx. Okay, now I use this as my, let's see, my x is my u, and the e to the x dx is the dv. Okay, So what I have here is UdV is equal to ultraviolet voodoo. Okay, so U times V minus the integral of V times du. So now I just use all my little pieces here. I say that the integral, remember, x is equal to u, dv is equal to e to the x dx. And now, using integration by parts, I know I can split up this integral into u times v, which is x times e to the x, minus the integral of v, so e to the x, times the derivative of u, which is dx. Okay, so I can see now that e to the x is, I can take the integral of e to the x, so I'm going to go ahead and evaluate that. So I have to rewrite everything. X e to the x dx is equal to x e to the x minus the integral of e to the x is e to the x times -1 plus c. And that is our integration right there. So we're splitting it up into something that we can actually integrate. Okay. All right, let's do another one. So we're going to do find the integral of x squared ln x dx. And what I know is that I need to assign something as u, and I need to assign something as dv. So I am going to try and make dv equal, let's make u equal to x squared, and dv is equal to the ln of x dx. But when I try to take the integral, I realize I don't know an integral for the ln of x. So even though x squared was an easier, it was easier for me to take the derivative of x squared, I can't take the integral of ln of x, but I can take the derivative of it. So I'm going to switch it. And I'm going to say u is equal to the ln of x. And dv is equal to x squared dx. Okay, so this part becomes my dv, and the ln of x is my u. All right, so I take the derivative of u, so du is equal to, the derivative of ln of x is 1 over x dx, and the antiderivative of dv would be 1/3 x to the third power. Right, and then I'll just double check. Yep, that works. I double check by taking the derivative. So 3 times 1/3 is 1, and then I reduce my power by 1. Okay, so I can go ahead and write this out now. I know that the antiderivative of u dv is equal to uv minus v du, ultraviolet voodoo. So x ln of x dx, that's the original, is equal to the ln of x times 1/3 x cubed minus the integral of 1/3 x cubed times 1 over x dx. Okay, let's simplify my integral here. So I get x ln x dx is equal to, and then I'm just going to rearrange this. I like to put the 1/3 x cubed before the ln of x minus the integral of, let's see, the x cubed over x is going to give me 1/3 x squared dx. And then I can go ahead and integrate the integral inside. So I get x ln x dx is equal to 1/3 x cubed ln of x minus, raise the power, and then you need to divide by that power. So 1/3 times 1/3 is 1/9 plus c. Done. Yay. Next, find the integral of ln of x. Again, we don't know the integral of ln of x. So we don't have a basic rule. Let's see if we can do this by integration by parts. Another thing that I see here is that we don't have a product. So what I'm going to do, I know I can't take the antiderivative of ln of x, so I'm going to make ln of x equal to u. And dv, I only have the dx left, so I'll just make that equal to dx. So this is basically 1 dx, right, times 1. So take the antiderivative of 1, I get x, and I'm going to take the derivative of u, giving me 1 over x dx. Let's go ahead and set this up. I have the integral of ln of x dx is equal to u times v. So u is ln of x times v, which is x, minus the antiderivative of v times du, voodoo. U times v du. Okay, so I end up with x times 1 over x dx for the v and the du. All right, let's simplify. Is equal to x ln of x minus the integral of 1 dx. Okay, so I get ln of x dx is equal to x ln of x, and we are going to evaluate the integral of 1. So the integral of 1 dx would just give me minus x plus c, since it is not a definite integral. All right, last one for this video, and then there'll be a second video. All right, I have, so sometimes when we assign a u and a v and do integration by parts, the integral inside your rewritten expression is not, you cannot take the integral of that, so we have to do integration by parts again. So I am going to start with taking the derivative of x squared. And one of the reasons why I chose x squared instead of sine is that eventually, if I take the derivative enough times, I'll end up with a derivative of 0. Whereas when I take the derivative of sine, it's just a cycle. It keeps giving me a different function. It's never ending. Okay, so I get dv is equal to the sine of x dx. Then I'll take the antiderivative, giving me negative cosine of x, and the derivative of u is du is equal to 2x dx. Okay, so next up, I'm going to say this is equal to u times v. So u is x squared times negative cosine x minus the integral of negative cosine x times 2x dx. And I do like to rewrite it. Okay. Write both sides of the equation. That'll be important later. All right, so I get negative x squared cosine of x plus the integral of 2x cosine of x dx. All right, now I have to deal with this business, this 2x cosine x dx, because I can't take the integral of that. So I'm going to set up a second integration by parts. I'm going to make u equal to 2x. I'm going to make u, we're going to call it u2. So du2 is equal to 2. And dv2 is equal to the cosine of x dx. So this part is v2 and dv2. And this part right here is equal to u2. Okay, so the antiderivative of dv2 is v2 is equal to the sine of x. And then so the sine of x takes the derivative, I get cosine x. I always double check that in my mind. Okay, so I'm going to go ahead and just rewrite this part over here on the side. So I have the integral of 2x times the cosine of x dx is equal to u times v. So 2x times the sine of x minus the integral of v, the sine of x, oops, forgot my dx, times 2 dx. All right? And what I notice now is that I can take the integral 2x sine x minus 2 times the integral of sine x dx. I can take the integral of sine, okay? The integral of sine would be negative cosine, okay? So I get 2x cosine x dx is equal to 2x sine of x minus 2 times negative cosine of x plus c. And I can see that these are going to make a positive. I'll just rewrite it for funsies. Is equal to 2x sine x plus 2 cosine x plus c. So I'm almost done here. What I need to do now is take my antiderivative, or the integral of 2x cosine x dx, and substitute it in to my other problem. So I just did a little side work. So what I get is, let me erase this because that line is in the middle of the page, is the integral of x squared sine x dx is equal to negative cosine x, x squared, that's not very nice. Okay, is equal to negative x squared cosine of x. So I'm taking this part right here, and then I'm going to write the altered form, the equivalent expression of the integral of 2x cosine x dx, which is plus 2 sine 2x sine x plus 2 cosine x plus c. And we're done. All right, so that's the first video. There's going to be a second one, so make sure you watch this.